this series, we're examining how modern sealer and adhesive technologies are used to extend the life of metallic products. And in our first snippet, we use the example of the automobile to outline the history of modern sealers and adhesives and to demonstrate some of the visible issues. In this segment, we'll look at the fundamental science that lies beneath controlling sealers and adhesives during application, how they compare to other fluid dispensing operations, and how they affect various application processes. You see, it's all about viscosity. All liquids change viscosity as a function of temperature, even water. It goes through a viscosity change of 2 to 1 between 10 degrees and 40 degrees C. You probably don't think of a glass of ice water as being thicker than a cup of coffee, but it is. So there goes that old claim that waterborne materials aren't affected by temperature. All sealers and adhesives follow the same pattern. And it's important to note that this is a physical property, not a defect. And therefore, we can use it to our advantage in our process. So here's the viscosity versus temperature curve for a typical sealer, but it could just as well be an adhesive. It's the curve we're all familiar with. When the temperature increases, the viscosity decreases, and conversely, when the temperature decreases, the viscosity increases. As we noted, this is common for all liquids, but if we compare this to common paints, for instance, we can see a stark contrast. Common paints will run in the range of 50 to 350 centipoise. Here we see that sealers and adhesive run orders of magnitude higher, often falling into the large range from 30,000 to over 1,000,000 centipoise. But what's really important about this curve is the steep portion of the curve from 18 to 26 degrees C. That's about 67 to 78 degrees Fahrenheit, so it's right in the middle of our ambient range. Here we can see that the viscosity falls from more than 8,000 centipoise to less than 4,000. Ironically, that's a 2 to 1 shift in viscosity over less than 8 degrees C. From this, it's easy to see how small variations in sealer or adhesive temperature will produce large changes in viscosity, which will have a significant impact on the performance of our process. As we noted in our first snippet, while robotic systems can repeat the gun path, speed, angle, distance to the part, flow rate, and total volume of sealer dispensed on every cycle, they can't compensate for the viscosity variations resulting from changes in ambient temperature that occur from morning to evening or season to season. As we see here, temperature-based viscosity variations directly affect the shape and bead or fan pattern being dispensed. Take the typical hem flange bead, for example. While you can see the change in the width of each bead, what's not shown is the height. Because each bead is comprised of the same volume of sealer, the change in width is offset by a change in height. The wider the beads, the flatter the beads. This is often referred to as spread or slump and can significantly compromise the function of the bead. Spray applications, like this anti-chip sealer, are similar. Here we can see the impact of temperature on dispense. The most obvious change is in the width of the fan pattern, but perhaps even more important is the impact of viscosity on spray consistency. Above 35 degrees, the coating is thin and uneven. You can see the substrate peeking through, but in the 30 to 35 degrees C range, the coating is smooth from edge to edge. This is probably the optimal operating temperature for this particular process. Below 30 degrees, we see heavy edges beginning to appear, which are often associated with striping on the finished part. As we move into the 25 degrees C range and below, we see the combination of very uneven coating surrounded by heavy edges. This makes it very difficult to get a smooth, even coating on the finished part. Without a smooth, even coating, both performance and appearance will be compromised. An operator must compensate for these changes by making adjustments to the pressure regulator or through eye-hand coordination, adjusting overlap and respraying thin areas. At lower temperatures, the heavy edges produce too heavy a film build in the overlap area, resulting in the sag issues discussed in the first snippet in this series. When robotics are employed, eye-hand coordination isn't even an option, and the problem can be repeated over and over again. It is essential to have exactly the right amount of sealer or adhesive in exactly the right place with precisely the right profile to assure proper performance in the application. And to produce the perfect bead or spray pattern, whether a manual or a robotic system, it's essential to dispense the material at exactly the right viscosity. This means controlling material temperature as it's being applied. We call that point of application temperature control, and often say that controlling the temperature at the nozzle is the only place that matters. In our next snippet, we'll look at the challenges of implementing accurate temperature control in a production environment and how those challenges were met by one of our customers experiencing significant issues with their application systems. I hope you'll join us.